Hi, this is my presentation on the Lab 3 black hole, where we attempt to find the mass of a black hole, a theoretical black hole, and the initial velocity that would be required for the ship that we are piloting to not crash in the black hole or veer off. To start out, we're going to discuss some laws of motion with added context to gravity and momentum. The first of which is that the rate of change of momentum over time is equal to the sum of the parallel and the perpendicular components. The parallel component is equivalent to the change of the magnitude of the momentum vector over time multiplied by the normalized unit vector for momentum. The bottom equation here is Newton's universal law of gravity, which states that the magnitude of net force is equivalent to the universal gravitational constant multiplied by multiply the masses of the two objects that we're dealing with divided by the distance between them squared. All right. So moving on to GlowScript to find our mass of our black hole, we use our random seed to generate our trajectory. And we set our star's mass and the time interval, which would be 1 day per the instructions in the Canvas document. Into our while loop in our trajectory, where we calculate our initial and final momentum that we will be using for our net force by multiplying mass times volume. And the change of momentum is equal to the change of momentum or change of time, which is also equal to the net force due to Newton's second law of motion. To calculate our parallel component for dp/dt, we use the equation mentioned before, and the perpendicular component is simply the vector minus the parallel component. And finally, to calculate the mass at that timestamp, we use the gravitational equation, just slightly rearranged to isolate m subscript bh. When we run it, we get values that I plugged into Excel, and the average of these came out to be 1.08 times 10 to the 34th. Moving on to the second part of our lab, we are on a ship and we have to figure out our initial velocity so we don't get sucked into the black hole. To do this, we calculate the net force on the planet and the net force on the spaceship to eventually plug into velocity and position update formulas. To find the net force, we again resort to Newton's universal law of gravitation, where we plug in the respective values to get the net force. Due to Newton's second law of motion, which states that force equals mass times acceleration, we can simply plug in force over mass into our velocity update formula. We found that a velocity vector of negative 6.3 times 10 to the 7th and negative 1.2 times 10 to the 7th meters per second will allow our ship to get close to the black hole and not get sucked in. To answer further questions for this lab, the parallel component of the rate of change of momentum represents the object speeding up or slowing down, and the perpendicular component of momentum, of the rate of change of momentum, represents the direction of our object. The rate of change of momentum and the net force mean the same thing. There's no difference. This is according to Newton's second law of motion. And if we wanted to have our ship completely orbit the black hole and not just avoid it, we found that reducing our x component of our velocity vector while increasing our vertical component would allow this orbit to happen. We got values of negative 2.3 times 10 to the 6 and 1.1 times 10 to the 7th. And this allows it to orbit without getting sucked in. Thank you.